Hello, this is Team UTD Comets. I'm Yug Singh,
And I'm Brittany Hernandez.
and today we will be presenting our findings for this year's Logic Locking Conquest.
Thank you, Yug. This is our background slide. It has information that helps understand our thinking and how we decided to go about solving the circuit. On the left here, we have a finite state machine, or an FSM, in both obfuscated mode and normal mode. The obfuscated mode hides the functionality of the entire FSM, while the normal mode is what the hardware is normally supposed to operate without being obfuscated. There are many ways to obfuscate the hardware, but the fundamental goal is to modify the hardware in such a way that its intent is indecipherable. An FSM has a limited number of states, and the structure of the hardware may be changed to alter the FSM's function as done in this challenge. A sequence of inputs, or a key, will be required to access the finite state machine's original function. What we're seeing here is a shift from one state, from the obfuscated mode, to the normal mode, and that will be important for us to find out how to get from one to the other. Here's our algorithm background, If a key sequence fails to unlock that finite state machine, it will remain in this obfuscated mode. Flip-flops are used to change or remain in a state. Therefore, they are our target for manipulation. Searching for elements in the Verilog code provided that are highly repetitive in relation to the flip-flops is a step towards finding the key inputs and added flip-flops. Here are some algorithm details. First, using the provided files, on Notepad++, the search and replace function is used to separate the wires by replacing comma with new space, replacing a new space after logic gates, and replacing the initial parentheses and the ending parentheses with a blank space. Now they can be read in a format that are separate lines. This is important because it can be fed into a program to get the counts of each line, and they can inform us on how many wires there are, how many logic gates there are, flip-flops, input data, output data, and more. The Oracle-based file is open and not key-bound, therefore the output can be simulated and the added flip-flops can be found. The small obfuscated file is our starting point for testing the algorithm since it is the shortest. Based on the repetition count file, the number of flip-flops in the Oracle-based file are 739 flip-flop 1 and 11 flip-flop 2. Any flip-flop that produces output data is valuable, and these are not considered added since the functionality depends on them. The most repeated wires will also not be considered added since they are important to the circuit function and they are vastly used everywhere. Therefore, the least repeated wires will be considered for removal and testing the code.
Thank you, Brittany. Now we'll go over our simulations themselves. After simulating the small circuit in Vivado, we were able to get the following output for running the default circuit with no modifications, as well as when we ran the circuit after removing the added flip-flops. As you can see, both of the outputs remain the same, therefore verifying that our algorithm actually works and the functionality of the circuit is still the same. To further reinforce the integrity of our approach, we present the output of a small simulated circuit when a vital flip-flop is removed. As you can see, the entire circuit loses its functionality. The outputs for the most part change to don't cares due to a vital signal being removed, which therefore changes the functionality of the entire circuit because it provides the wrong output. Lastly, our findings. After running our algorithm recursively, we were able to pinpoint the added flip-flops. And here we have presented a couple of them. That's all we have for today. Thank you very much for your time.
Thank you.